This is a video for the limits test review in Calculus with Applications. So the first part, use a graph to estimate the limit. Since this 2 here doesn't have a from the left or from the right, I have to look from both sides to see what value we're approaching. So from the left, the graph is approaching a y value of -3. From the right, the graph is approaching a y value of -3. So that means the limit from both sides is -3. In part B, from the left, we're approaching a y value of 2. And from the right, we're approaching a y value of 1. So from both sides, this limit does not exist because we're approaching different y values. So this limit is at -1, which is here. Whoa, that's not straight. Let's try that again. Close enough. So I can see it's from the left and from the right. Both limits from the left and from the right are approaching a y value of 2. Find the limit. So this hint of use direct substitution, that will not be on the test. I know to use direct substitution if I can plug in the approaching value and get a number that's not undefined, not square rooting a negative, not dividing by 0. So if I take -3 in for x, that's -2 times 9, which is -18 plus 1. So this limit is -17. -1. So simplifying this is going to be 1 minus 2 plus 3 and 1 plus 1. So in my numerator, I've got 2 over 2 for the denominator. 2 divided by 2 is 1. And let's try here, 3 squared. So that's just the square root of 5. For this next section, it says use a cancellation technique. So one piece to clarify, you will not have to factor the sum and difference of cubes like this on the test. You will have to factor quadratics, something with an x squared, a difference of perfect squares. So we're going to practice the factoring now. So if I go straight for the substitution method, if I take -1 and plug that into the denominator, we get an expression that's divided by 0. And dividing by 0 is undefined, but the limit may not be undefined. Because the limit is just what y value are we approaching. So let's see, because I'm going to use the cancellation technique, which means I think there's going to be a hole where a factor in the numerator divides with that denominator. So what multiplies to -1 what multiplies to -6 that adds to -5. So my choices are 1 and 6 or 2 and 3. To add to a negative, the bigger number is negative. So we're going to have to go with 1. So +1, -6. And sure enough, x plus 1 divided by itself is 1. So this problem really is the limit as x goes to -1 of x minus 6. It's the only factor remaining. So I can plug in -1 and we get -7. So in B, you will not have to factor a sum and difference of cubes. I've typed out the factoring here. So you can see x minus 5 divides by itself. So we've got the limit as x approaches 5 of x squared plus 5x plus 25. So if I plug in 5, So that's going to be 25 plus 25 plus 25. So we get a limit of 75. One last expression to factor. X squared minus 4 is the difference of perfect squares. So that factors to x minus 2, x plus 2. The x plus 2's divide, so we're left with the limit as x approaches 2 of x minus 2, which is 2 minus 2, so we get 0. Find the limit. A sketch will be helpful. So, because these limits, where's my highlighter? Are from the right, from the left, from the left, having a graph would be helpful. So I'm going to bring up my calculator. I'm going to clear out what's here and make a graph. I'm going to use zoom 6, which is a 10 by 10 in every direction. I'm going to hit trace. And I'm going to go find where, actually, I'm going to hit trace 3, enter, and that tells me the point 3, 1. Okay, so from the right, so coming from the right, this y value would be 1. If you want to see that. So from the right-hand side, we are approaching a y value of 1 when x is 3. All right, let's do the next one. So I'm going to hit trace 1, since we're approaching x is 1. And that's the endpoint of this square root. Oops. And the limit from the left would be over here. But there is no graph on the left. So I cannot approach the x value of 1, which was here, from the left-hand side. So this limit does not exist. All right, last one. Absolute value. I'm going to hit the math button, arrow over to number. ABS stands for absolute value. I have to group my denominator. I actually have to group the numerator too, but that ABS actually does the parentheses for me, so I don't have to make sure to do that. I'm going to hit graph. All right, and then if there's the x value of 7, so I'm going to go trace 7, enter, and that's where this jump occurs. So the little negative is left of 7, so let me trace to 6.9. Aha, so that's this top piece. So as we approach 7 from the left, this y value is 8. You can see that right here, 8. All right, find the limit if it exists. And for part 5, we have all these x's approaching infinity. So this is really end behavior with infinity. And in your packet, we wrote out the different rules about comparing the numerator and denominator. So when the powers the highest power, meaning the degree. When this highest power are equal, we divide the leading coefficients for the end behavior. So 3 divided by 1 is 3. We have to be a little more careful in part B, because here's a degree of 1 and here's the degree of 1. So our leading coefficients are 3 and negative 3. So 3 divided by negative 3 is negative 1. And C, the denominator is not in standard form. So x plus 2 squared means x plus 2 times itself. And if we were going to multiply this out, I'd get x squared. And then the rest of that polynomial. But I only care about this highest power. So we have a power of 1 here, a power of 2 in the denominator. So when the numerator is smaller degree than the denominator, our limit, our end behavior is 0. Find each limit if it exists, sketch a graph. Okay, so for this first graph, there's pieces. And as I sketch it, I'm only going to sketch each piece for when x is less than 0, or this piece when x is greater than 0. So let's start. We got x squared plus 1. So when I hit graph, I'm going to get the entire graph. And I don't want the entire graph of x squared plus 1. I only want x's less than 0, which are over here. So I can see that vertex is at positive 1. This less than or equal means this would be a closed point. I'm going to hit trace. Let's go to negative. Okay, negative 2, that works. Negative 2 is at 5. And we get this parabola. Shape. And then I'm going to graph 2x minus 3. Let's see where it's, if I hit trace 0, that shows me the y-intercept is at negative 3. And not or equal means this would be an open circle. And then so if I just hit the trace button, I notice hey, we have all these crazy decimals. So let's trace to, I don't know, 2. All right, so at 2, we have a y value of 1. So I get this ray. And now, because the limits are all at 0, I'm going to focus here when x is 0. From the left, that's this side, over here on the parabola, from the left, my y value is approaching 1. This y value is 1. From the right, my y value is approaching negative 3. These numbers are different, so the limit from both sides does not exist. All right, math, number, absolute value, x plus 3, x plus 3. So it looks like our jump is over here at negative 3. And at negative 3, if I hit trace, negative 3, enter, there is no y value. So there's a hole on this side and a hole on this side. And the y value is 1. Down here it would be negative 1. If you're not sure, trace to the left. There you go. You can see it's negative 1. So from the left at negative 3, which is here, from the left, we have a y value of negative 1. From the right, we have a y value of positive 1. These values are not the same, so the limit from both sides does not exist. All right, so we need a table of values for this problem because if I try to plug in -1, we get divided by 0. That's undefined. We can't do that. If I factor the denominator, none of the factors will divide to 1 and simplify. So I have to use a table to look really, really, really close to -1 to see what the limit is approaching. When I type this into y1, I need parentheses around my numerator and my denominator so that the calculator knows I want to divide the entire expression. And for the first time I'm making one of these tables, I'm going to go to second window. I have to set my independent to ask, so my calculator is already set up for me that way. If yours is not, arrow down to ask and hit enter. Then I'm going to go to second graph, which is my table, and delete out all those values. And now I'm going to type in these values. So at -1, we cannot evaluate this expression. That's undefined. The calculator says error. And you're not turning in your calculator with your unit test. So you should copy these numbers onto your paper. I'm going to take a shortcut. Okay, so I've got my values here. And these, the -1.1, -1.01, these values are from the left. And I can see from the left, I'm approaching -0.25. Now, if I move my cursor, it's not really -0.25. It's not a quarter exactly. The calculator gave up and just said, I'm going to truncate this and round it in the table. There's only so much space. So it's really 2.49937 and so on and so on. Same thing with this value here. But because the calculator's truncating it for us, I can see from the left and the right, both of those values are approaching -0.25, which is the same thing as -1/4. All right, let's do the same thing again for B. Parenthesis around the numerator, parenthesis around the denominator. My table's already in ask, so I'm going to come in here and delete all these out. Got my numbers from the left, my numbers from the right. So if I look really, really close, just at around 3 here, I can see that it looks like it's the decimal 0.16 repeating, because the 667 or the 6668. So it looks like 1.6 repeating. If you're not sure what that is as a fraction, we can trick the calendar in to doing that for us. I'm just going to type a whole bunch of 6s here. And then I'm going to go to math, change that to a fraction. We get 1/6. This problem actually could have been done with the substitution method. I can factor that denominator to x minus 3, x plus 3. And when I do that, and the x minus 3's divide to 1, I'm left with 1 over x plus 3. So when I take my 3 and substitute in, there's that 1/6 value for the limit. Sketch a graph and discuss any type of discontinuity. Okay, so our choices are point, which is a hole, jump, which is a jump, and infinite, which is a vertical asymptote. So I'm going to put A in my calculator. Don't forget the parentheses around your numerator and denominator. And I don't know, that looks continuous to me. If I sketch that, it does not look like there's a discontinuity. But you are smarter than your calculator, and we need to do a little bit more investigating. When I look at this equation, I can see that there's an undefined value. We can't divide by 0. So x plus 1 can't be 0, which means if I solve this, x cannot be negative 1. So in my calculator, if I hit trace negative 1, look, there's no y value. Calculator is not sophisticated enough to draw you a hole. It's just not going to show it. So you have to stop and think and go, oh, there's a value that this graph is undefined at. Even though the calculator makes it look continuous, there's an undefined value at negative 1. This one's a hole. So out of the choices of point, jump, or infinite, we would call this one a point discontinuity. All right, we've got the next one. Did I type that right? Yes. All right, so for this graph, again, I know that I cannot divide by 0, so at x equals 3 would be a discontinuity, because that's what would make the denominator 0. So I count over, here's my third x, 3 for x. That's that vertical asymptote, which is an infinite discontinuity. See, we've seen a bunch of these absolute value graphs already. Let's type it in just to be clear on what it looks like. Just by looking at this graph, this equation, I know x can't be 6. That would make the denominator 0. So sure enough, 1, 2, 3, 4, 5, 6. Here's x is 6. And again, your calculator is not sophisticated enough to draw these open circles at the end. But this is the jump discontinuity. And I think that is the end of our test review. To know you're ready for the test, you should be able to do all these problems without the video, without the answer key, to know that you are ready to go.